Voyager 1, launched in 1977, is the most distant spacecraft ever sent from Earth. It is moving away from us at a speed of about 38,000 miles per hour, or roughly 11 miles per second. Despite its staggering distance of about 15.5 billion miles from Earth, we are still able to communicate with it. So how is it possible to send commands to such a distant spacecraft, or receive data from it? And how much longer will we be able to stay in contact with Voyager 1? Voyager 2 was actually launched first on August 20, 1977. Voyager 1 followed about 2 weeks later, lifting off on September 5, 1977. Voyager 1 and Voyager 2 are nearly identical in design. Their mission was to explore the outer planets beyond Jupiter. Rocket engines alone could not provide the necessary speed, so mission planners chose a rare planetary alignment that allowed the spacecraft to gain speed by using the gravitational pull of multiple planets. Jupiter, Saturn, Uranus, and Neptune were lined up in the same general direction as seen from Earth. This alignment will not occur again until the year 2150. Voyager 1 flew past Jupiter and Saturn, sending back breathtaking images along the way. This image shows the atmosphere of Jupiter. It also confirmed the presence of Jupiter's faint rings. Voyager discovered active volcanoes on Jupiter's moon Io. It then headed towards Saturn. There it observed Saturn's rings from a close distance and discovered shepherd moons that help shape and maintain the rings. It also found that Saturn's moon Titan has a thick atmosphere composed of about 90% nitrogen. After their planetary encounters, Voyager 1 began its long journey toward the outer edge of the solar system. Voyager 2, however, was on a different trajectory, one that took advantage of a rare planetary alignment. This grand tour path allowed it to fly by Uranus in 1986, and Neptune in 1989, destinations Voyager 1 would never reach. Its cameras captured the first-ever close-up images of these ice giants, revealing tilted magnetic fields, dark rings, and a host of new moons, forever changing our understanding of the outer solar system. Interestingly, despite launching 16 days its twin, Voyager 1 is now much farther from Earth. This is because its path was designed for speed, using powerful gravity assists from Jupiter and Saturn to slingshot it ahead. Today, Voyager 1 is hurtling through space at over 38,000 miles per hour, or about 10.6 miles per second. Voyager 2 travels at a slightly more leisurely 35,000 miles per hour, or 9.7 miles per second. That speed difference of 0.9 miles per second may not sound like much, but over cosmic distances it adds up. In just 1 minute, Voyager 1 pulls nearly 54 miles further away from its twin. Decades after their launch, both spacecraft achieved a monumental milestone. They exited the heliosphere and entered interstellar space, becoming the first human-made objects to do so. It's important to understand that the heliosphere and the solar system are not the same thing. The heliosphere is a vast, protective bubble created by the solar wind, a constant stream of charged particles flowing outward from our sun. This bubble shields the planets, including Earth, from the majority of harsh galactic cosmic rays. As our sun moves through the galaxy, this bubble gets compressed in the direction of travel and stretched out behind, like the wake of a boat. The edge of this bubble is called the heliopause, the point where the sun's influence gives way to the vast, mysterious realm between the stars. Voyager 1 and Voyager 2 have both crossed the heliosphere, a monumental achievement marking humanity's first direct contact with the medium between the stars. Voyager 1 crossed this invisible frontier in 2012, followed by its twin in 2018. This graph shows actual data from Voyager during that moment. The lower graph shows the number of solar origin particles plummeting as the spacecraft exited the sun's magnetic bubble. Simultaneously, the upper graph shows a sudden increase in high-energy galactic cosmic rays, particles from interstellar space. For the first time, we were directly sampling the cosmos beyond our solar neighborhood. But leaving the sun's influence doesn't mean leaving the solar system. The solar system itself is much larger. Far beyond the heliosphere lies the Oort cloud, a colossal, theoretical sphere of icy planetesimals. This immense shell of trillions of icy bodies and rocks surrounds our sun. While we've never observed it directly, its existence is inferred from the orbits of long-period comets. According to some estimates, it will take Voyager another 300 years to enter the Oort cloud and about 30,000 years to exit it, by which time it will be a silent relic. Yet for now, we can still send commands to the Voyagers and receive scientific data from them. This ongoing dialogue is an incredible feat, but how is communication possible over such vast distances? The key is the spacecraft's high-gain antenna, a prominent 12-foot parabolic dish. This antenna is the Voyager's voice and its ear, responsible for sending data and receiving commands. To work, it must be aimed with pinpoint accuracy toward Earth, a tiny target in the distance. The antenna emits a very narrow beam of radio waves with just 22 watts of power, the equivalent of a refrigerator light bulb. This faint whisper travels at the speed of light, but the journey is long. It takes about 22.5 hours for a signal to reach Earth. For comparison, it takes just over 1 second for light to travel from the Earth to the Moon, and about 20 minutes to reach Mars. This puts the Voyager's distance, and the nearly 2-day round-trip communication lag, into perspective. Radio waves weaken with distance following the inverse square law. As the signal spreads out, its strength plummets. So by the time Voyager's 22-watt signal reaches Earth, it has faded to just a tiny fraction, less than a billionth of a trillionth of a watt. The energy arriving is 20 billion times weaker than that of a standard digital watch battery. Detecting this is an extraordinary challenge. To detect such faint signals, NASA uses the massive antennas of its Deep Space Network, or DSN. These antennas are 230 feet in diameter, their sheer size crucial for gathering every possible photon. To increase sensitivity, the receivers are cryogenically cooled to minimize electronic noise. The network is set up at 3 locations: California in the United States, Madrid in Spain, and Canberra in Australia. This ensures that as the Earth rotates, at least one antenna can always see the spacecraft at any given time, enabling 24-hour communication with our farthest explorers. But transmitting data and running instruments requires power. Far from the sun, where its light is hundreds of times fainter than at Earth, solar panels are useless. Instead, Voyager uses nuclear power. 3 radioisotope thermoelectric generators, or RTGs, convert heat from the natural decay of plutonium-238 directly into electricity. This ingenious system, with no moving parts, was designed to provide reliable power for decades, enabling its journey into the depths of space. At launch, each Voyager produced over 470 watts of power, but this output predictably declines by about 4 watts each year, due to the plutonium's decay and aging hardware. Now, after decades of flight, power output has dropped below 200 watts. To conserve energy, non-essential systems and instrument heaters have been shut down gradually in a careful strategy to keep the mission alive for as long as possible. This power-saving imperative led to one of the most famous photographs ever taken. This is the pale blue dot, a photo of Earth taken by Voyager 1 in 1990 from nearly 4 billion miles away. It was the last picture Voyager 1 ever took. After capturing this final, humbling look homeward, its camera was permanently turned off to save power for its primary mission, the journey into interstellar space. Voyager 1 originally carried 10 scientific instruments. Today only 4 remain active, chosen to study the interstellar environment. These instruments measure magnetic fields, count charged particles from deep space, and listen to the waves in interstellar plasma. With just these senses, Voyager continues to be our probe in the space between the stars, sending back data from a region humanity has never before touched. Over the decades, the Voyagers have encountered some heart-stopping technical issues. In 2023, Voyager 2 experienced a problem when a mistaken command caused its antenna to drift off by just 2 degrees. That may not sound like much, but at billions of miles away, that tiny angle shift is critical, and the communication link was completely severed. For weeks, the probe was silent. Fortunately, NASA had anticipated this scenario. Voyager was pre-programmed to automatically correct its orientation a few times each year. Sure enough, it reoriented itself and communication was restored. Engineers are also planning for future problems like thruster valve blockages. The small thrusters that aim the antenna can clog after decades of firing, requiring clever, long-distance workarounds to keep the spacecraft talking to Earth. Despite these challenges, both Voyagers continue their journey and maintain communication with Earth. However, their time is running out. As they get farther away, their signal strength declines while their power supply dwindles. NASA expects that by 2036, communication will likely end. At that point, the Voyagers will fall silent, continuing their journey into the galaxy as our silent ambassadors for millennia to come. Voyager 1 and Voyager 2 were launched in 1977. Their mission was originally planned to last only 5 years. However, they have been operating for more than 40 years, far exceeding the initial plan. The memory capacity of the Voyagers is about 13 millionths of that of a modern smartphone. Their communication speed is about 138,000th of today's standard. Although the technology was state-of-the-art at the time, it has now become outdated. Despite carrying old equipment, these probes have reached the farthest points from Earth and represent the forefront of space exploration. By transmitting very weak radio signals, they stay connected to Earth and will continue to travel through unexplored space in the future.